Hi, and welcome to 15.3 Index of Refraction. In this lesson, we talk about what happens to light as it enters mediums that have different, they're like different optical densities. So, numbers 1 and 2 kind of talk about what happens to just waves in general, even as they enter new media. So, one of the things that we talk about is how the frequency is the DNA of the wave. So it makes the wave whatever it is. So if you look at that electromagnetic spectrum, you could go all through the spectrum and have all different frequencies. And depending on what the frequency is, that's the type of like light that you're looking at or radiation. So green light is going to look green even if it enters a new medium. The only way that can change is if there's an observed change in frequency due to the Doppler effect. Then the frequency, you could get like a longer wavelength or a shorter wavelength, and that would affect the frequency, which makes the light look different. That's like red shift and blue shift, which we talk about in 15.5, I believe. So frequency is the DNA of the wave. And what happens is we have two mediums. And you might ask yourself, well, why does frequency have to stay the same? Remind yourself what frequency is before we talk about this. It's how frequently the waves go by. So there's going to be a certain number of waves every second. For simplicity, let's say that there's one wave that goes by every second. So as this light is coming in, we'll use this transverse wave here. Well, you see how my pen was going up and down? Think of this as like a rope. And right now there's molecules in this rope here. The rope wants to stay together, like intact. So you're going to get one wave that's passing by every second. And this is like vibrating up and down. And the rope is vibrating up and down. You can't just all of a sudden disconnect here and be like, okay, it's going to be a higher frequency now. Okay, closer together, whatever it is. All right, the rope has to stay the same place. So even though it enters a new medium, let's say now this medium makes it go slower. Well, if the rope has to stay intact here, and we have a velocity coming in, but now it's going to go slower, all right, they're going to kind of stack up on each other. And this rope will still vibrate up and down the same number of times per second, but now the velocity is less. All right, so it's still going up and down. It's still moving to the right, but it's going to slow down. So what you get is a smaller wavelength like this. Okay, it's still the same number of waves passing by you every second, but the wavelength is smaller now. And we can see this relationship between the velocity and the wavelength in our wave speed equation. V is equal to F lambda. Well, if we said that the frequency has to stay the same, if the velocity got slower, what happens to the wavelength? It's a direct relationship, so the wavelength decreases. It gets smaller. What happens if it gets faster? It enters a medium and it's getting faster now. So now it's going to speed up. It goes faster in this new medium. So let's say it's going from like water, it starts in water and it's going into air. Then the velocity will get bigger. And what's going to happen if the waves are coming in 1 cycle per second, so it's 1 hertz, but now all of a sudden the waves are able to move way faster. All right, so you're still going to get the same up and down 1 cycle per second, but it's going to go faster now. So it's going to go, whoa, super fast. Okay, and now you could see the wavelength. What happens between two successive points on the wave? Boom, super long wavelength now. So the velocity increased, therefore the wavelength increased. All right, but the frequency stayed the same. And by the way, if you look at number one, if the frequency is staying the same, they're asking about the period now. And if the frequency is the same, that means the period is the same. T is equal to 1 over F. If F stays the same, then the period stays the same. So number one, as a monochromatic light ray passes from air into water, two characteristics of the ray that will not change are the frequency and the period. the wavelength is going to change, and the speed will change. Number 2, the wavelength of a wave doubles, so it's getting bigger. So the wavelength is, let's say this is double. This is lambda, this is 2 lambda. It's getting twice as big. As it travels from medium A into medium B, compared to the wave in medium A, the wave in medium B has twice the speed. And we could again see from the V is equal to F lambda formula, if you want to do it mathematically, you could say, oh, well, if I double the wavelength, I have to double the speed as well. Number 3 says the speed of light in a material is 2.5 times 10 to the 8 meters per second. What is the absolute index of refraction of the material? So first of all, you have to know what they're looking for. The index of refraction, we use the letter N. That's what they're asking for. And there's actually another piece of hidden information that you don't see the number there, but you should know that you have to use it, because we know the speed of light in a vacuum is always going to be 3 times 10 to the 8 meters per second. And that's going to help you in this formula, which is on page 5. So this is the formula that we're using today. In 15.4, we're going to use Snell's law. And then you could use this once we use, even right now, if they had a question like that, that's fair game as well. So N is the index of refraction, and you could find this on the table. I think it's page 2. Yes, page 2 lists the indices of refraction for all these different types of material. All right, and it's on the same page as your other electromagnetic spectrum wave type stuff. So that's kind of convenient. And what these numbers represent, you saw the formula before. The index of refraction is equal to C over V. It's just a ratio of, well, this is always 3 times 10 to the 8 meters per second, because that's the speed limit of light in a vacuum. That's as fast as anything can go in the universe. And then as it enters a new material, any of these, as it enters a new material, it's going to slow down. Okay, so let's say it slows down to 2 times 10 to the 8 meters per second. Well, you could get this ratio, and it looks like it's going to be 3 halves. So 1.5 would be the index there. So it's close to crown glass or something like that, or lucite. Okay, so that's the idea there. It's just a ratio of, okay, how much did it slow down? And this is a piece of hidden information. A lot of times in the problem, they'll tell you for a specific frequency of light. That's a hint that you're probably going to have to look at the index of refraction table. The light bends at different amounts depending on the frequency, so they're just like kind of doing their due diligence in telling you that you can use this table there. So now we could use the equation, substitute, and solve. Now make sure that you're plugging this into your calculator with either parentheses, or you could do 3, the capital E button, and then 8. And then that takes care of the parentheses for you, because PEMDAS will come into play. And if you don't use the parentheses or the E button, you'll get a different answer. So the index of refraction for this material is 1.2. If you want to be fancy, you could do 1.20, because the table rounds everything to the hundredths place. So there you go. Number 4, which quantity is equivalent to the product? Remember, product means multiplying. So which quantity is equivalent to the product of the absolute index of refraction, N, of water, and the speed of light in water? So the speed of light in water is V, and we're looking for the product of these two things. What is N times V equal to? Well, you got to look at an equation with N and V. And this whole lesson happens to be about this equation, N is equal to C over V. Imagine if this was just a random Regents question that you had at the end of your exam out of nowhere, and you weren't typically thinking of this right away. Man, that would have been tricky. This is a Regents question. So N times V, when you cross multiply, okay, C is equal to N times V, the speed of light in a vacuum. So that's choice D. Tricky stuff. Tricky stuff. All right, number 5 is a whole lot of fun filling in this table, and then we get some cool stuff over here. I'll do a couple with the table. Let's see. It says fill in the table below by finding. This is interesting. So this is the table from the reference table. It's all the same stuff in the same order. And then the goal is to find, how fast is it actually going? Because yes, we know what the index is, but it'd be kind of cool to know what the speed of light is. So I'll do the first one. The first one is done. Well, I'll do this one here. Oh, I didn't say before. Why is air only 1? It's actually 1.000, and then there's like another number. It's very close to the speed of light in a vacuum. Air's not going to slow down light that much. So that's why the ratio is very close to 1. But if you round it out all the way, it's not exactly 1. Anyway, let's find the speed of light in corn oil. So we know that N is equal to 1.47, and C is always the same, so it's 3 times 10 to the 8. And we're looking for V, so this is meters per second. So you're going to do N is equal to C over V every single time. But instead, why don't we solve for an equation? What does it look like when we solve for V? So let's cross multiply like we did above. C is equal to N times V. And if we divide out the N, we have a handy equation for V. So if you do V is equal to C over N, it's kind of like the same thing every time. So for all of these, you just do the speed of light in a vacuum divided by whatever that number is in your calculator, and then it'll pop out all the different numbers. So if you do like if you hit second entry in most calculators, it's like, I think it's near the equal sign, second entry, and then it'll put the equation in again, and then you just move your arrow key over, and you could write a different number over here. And it'll make it easy to fill in the whole rest of the table. So I'll just show my work for one of them and then plug in all the numbers for the rest. So I got 204081632.7 meters per second. That's very precise. Notice how they weren't precise in even the reference table. We don't want you to be this precise, because chances are that's actually inaccurate if you were going to scientifically do an experiment. The corn oil might have a very slightly index. You can't really get that precise under normal laboratory settings. So we'll just round it to this, and we'll call that more than close enough. And then we'll do the same thing. So you take speed of light in a vacuum divided by the index of refraction. That'll pop out the speed of light in that particular medium. And this is the speed for all these different mediums that are in your reference table. And there you go. So hopefully, as you can see, the higher the index is, what happens to the speed? It's going to be very slow. So as the index increases, if this increases, that means that the velocity decreases. It's an inverse relationship. And as you can see, diamond has the highest index on our table here. It's going to slow down light the most, from 3 times 10 to the 8 to only 1.24 times 10 to the 8. So that's that. And now let's put it to practice. So it says in the diagram below, monochromatic light of 5.9, it should be times 10 to the negative 7 meters. In air is about to travel through crown glass, water, and diamond. So they're telling you, it looks like the wavelength of that, and if you found the frequency, I'm sure it would match up to the one that's in your reference table up above here, 5.09 times 10 to the 14 hertz. So if you did the V equals F lambda with this as your lambda, should be that. So yeah, again, they're telling you the wavelength here. In which substance, this is, as you can see from the diagram, this is a very old Regents question. So that's why maybe back in the day they might have used it, the wavelength instead of the frequency in that table. This is like 1980s, I think. In which substance does the light travel the slowest? Really, you're just looking over here. Who cares about all that other stuff? But really, it's telling you, they're telling you this so that you could look at that part of the reference table, and we want to know where it's traveling the slowest, diamond, water, or crown glass. So we had diamond, water, or crown glass. Where is it traveling the slowest? Well, we calculated everything, so that's nice. So we know it's diamond. But if you were just looking at the table on your reference table, you would look for the highest index. All right, so which one of these has the highest index? It's going to be diamond. Oh, and then air's in there too, but air is only 1, so that's actually going the fastest. All right, so we wanted the slowest. Okay, that was right. Number 7, in a certain material, a beam of monochromatic light. This is more like it. This is definitely telling you to use that absolute index of refraction thing. It has a speed of 2.25 times 10 to the 8 meters per second. The material could be what? So we actually calculated the velocities for everything, but if you didn't have the velocities for all those different things, what you would have given to you in the problem is the velocity of the light, hidden information for the speed of light in a vacuum, and they're asking you what the material could be. And if you notice all this other stuff, then you should be thinking of the index of refraction, like glycerol, flint glass, crown glass. We don't really see that anywhere else on the reference table. So you should be thinking of, oh, well, if I wanted to know what that material is, if I find out what N is, then I could use my reference table and it'll tell me. So we're going to do N is equal to C over V. And you get 1 1/3. Oh, by the way, I didn't say this before, but what are the units for the index of refraction? Well, you do a meter per second divided by a meter per second, so there actually is no units. So that's kind of cool. So we're looking for 1.33 repeating, and I just so happen to have it circled already over here. Water. Water has that index, so we're going to go with choice D. In which way does blue light change as it travels from diamond into crown glass? Is the frequency changing or is the speed going to change? Well, we said before that the frequency stays the same. It's the DNA of the wave. It's what makes the blue light look blue. And just because it goes from diamond into crown glass, that's not enough to change its color. So we want to see, okay, diamond into crown glass. Here's diamond here. Here's crown glass here. So it's going from diamond into crown glass. It's going from a higher N to a lower N. And it's an inverse relationship. So that means it's going to go from a lower speed to a higher speed. It's going to get faster as it enters crown glass. Just remember that in diamond, it travels really slow compared to everything else. So the speed is going to increase as it enters crown glass from diamond. Number 9, last one. It's a graph. A ray of light travels through various substances. Which graph best represents the relationship between the absolute index of refraction of these substances and the corresponding speed of light in these substances? Any of these graph questions, again, you want to pull out the two things they're comparing, the index of refraction and the speed of light through the substance. So that's not C, that's V. So how are N and V related? We kind of said it before. But now that you know the two variables that you want to relate, you find an equation that relates the two of them. We'll use N is equal to C over V. Then you identify what is the relationship between my two variables. Since they're on opposite sides of like the fraction thing, we're going to call it an inverse relationship. Inverse relationships look like this because as one gets higher, the other gets lower. That's inverse. So we're looking for choice D. Okay? And that's about it for 15.3. Have a great day.